Yeah, so I'll be talking about checkpointing for supercomputing. Um, so Gene talked about DMTCP at a high level yesterday. Um, so there were some obvious questions about the performance overload of DMTCP. So I tried to address those questions in this presentation. Um, Having said that, this is still a work in progress. So that's what the title says, and these are very preliminary results. Um, and I have to acknowledge that most of it is Jiajun's work actually. I would say probably 90% of it is Jiajun's work. He couldn't make it to the presentation, but anyway. So, okay, so next, so this is just a brief overview of what I'm talking about. I start with trying to look at the state of the art in the checkpointing space. Then I'll talk about our approach to checkpointing, which is DMTCP. Then we'll come back to basically the motivation for this work, and then some concrete numbers at MGHPCC. So MGHPCC is is a research cluster in Massachusetts. This stands for Massachusetts Green High Performance Computing Center. It's a joint venture between the universities in the Boston area. Then some of the recent results from Stampede. So then some of the things that we have done from the results that we have got so far. So some experiences, I'll share some experiences. Okay, so next. So this was just a brief overview of the checkpointing space currently. So at one end we have application-specific checkpointing. The application developer obviously knows their application best. So they know the data structures. They can obviously add code to simple fault tolerance and checkpointing. So at the other end you have transparent checkpoint solutions. So BLCR is I think one of the oldest tools. It's a single process solution. So MPI implementations and resource managers have obviously had a host to integrate BLCR. So one of the recent tools is Group, which uses Linux containers and namespaces. And then obviously we have DMTCP, which works transparently, so you don't have to modify the user application or the client system. It works for distributed applications, including it also supports TCP and InfiniBand. A brief overview of DMTCP. So DMTCP is a distributed multi-threaded checkpointing package. So as the name suggests, it supports distributed applications out of the box. It works entirely for user space. You don't need any super user privileges. So because it sits at low level, than MPI, we can support most MPI implementations out of the box. So specifically for the HPC audience, we have recently added support for various resource managers. So there's a resource manager plugin that allows you to checkpoint your interactions with the resource manager. We also have support for checkpointing InfiniBand. So you don't have to bring down your InfiniBand network in order to checkpoint. Let's see. As is probably true for any system software, DMTCP has gone through various generations. of architecture. Starting with monolithic software, which we quickly realized would scale way too for, there's always the next kind of external resource that we want to checkpoint. But what we've currently set down to is this architecture where we have reduced the DMTCP's code checkpointing to about 22,000 lines of code. And this allows us to rapidly support different kinds of external resources. So particularly for HPC, we have this InfiniBand plugin, which is like 8,000 lines of C, C++ code. And of course, we have the resource manager plugin. Okay, so yeah. So take a step back, looking at the motivation of why we are actually doing this. So back in the day when we had a disk per node, taking a full memory dump, which is what DMTCP essentially does. I mean, there are some obvious optimizations that we do for 0 pages, many other things, but it's basically a full memory dump. So yeah, when you have a disk per node, it was pretty easy to do that. But with backend storage, many compute nodes are trying to run to use the same channel, so bandwidth to the disk is limited, so it's no longer efficient. But the good thing, however, for us is that with SSDs, this is no longer a problem. So the point is that DMTCP style checkpointing can be practical in the future, and we obviously want to plan for it. So yeah. Okay, so some actual numbers. So there are two kinds of overheads with DMTCP. One is the runtime overhead. So DMTCP works by interposing non-certain calls using this dynamic linear options of LPO. So there's obviously some overhead during the runtime, but but if you have a computationally intensive process, it's usually amortized over the run of the process. So what we're seeing here is the numbers for the NAS in benchmark. There is some overhead, and we have identified the bottlenecks within the TCP for these overheads, but for most of the cases, when application is run for a long duration, it's obviously the overhead obviously is amortized over time. So yeah. So as far as the checkpoint times are concerned, so again, okay, so I forgot to mention this actually. These numbers are not with MVAPICH, but with OpenMPI. So these are not a few months back actually. These are not recent results, but I did want to put these results in the slides. Okay, yeah. So coming back. Checkpoint times are usually dominated by the time it takes to basically the bandwidth to the disk, the time it takes to for it to dump the checkpoint has to the disk, the process of memory to the disk. So as the disk size decreases, we do see decrease in the checkpoint times. So yeah, I want to skip that and come to the results from Stampede. So these are more recent results. So starting with micro OSU micro benchmarks. So yeah, I want to focus on some of the overheads from the InfiniBand plugin. So again, InfiniBand plugin is required if you want to checkpoint an application that uses InfiniBand. It's it's not required for running your application, but if you want to checkpoint that application, you would require the InfiniBand plugin. So there are 4 plots over here. In each plot, you have 3 different timings. One is when I'm running the application natively, that's without DMTCP, which is the green one. Next is the when I'm running the application with DMTCP but without the InfiniBand plugin, which is the red line. And finally, we have DMTCP plus InfiniBand plugin. So when I'm running the application with DMTCP and the InfiniBand plugin, which is required for checkpointing. So this is probably not the best way to represent these results, but yeah, I want to look at a big picture over here. So what we're seeing here is that it doesn't quite fit the latency, but we are seeing some performance degradations when using the InfiniBand plugin in bandwidth. So the bandwidth does drop by about 30% in some cases with the InfiniBand plugin. So we did some profiling of the InfiniBand plugin, and it looks like it involves a lot of mallocs, which we plan to fix in this fall. So yeah. Okay, so this is the macro benchmark. So this is the runtime overhead with the mass L2 benchmark. 2 things to note here. So for numbers from 2 to 1K processes, we used the default MVAPICH 1.9 at Stampede with this NV2 on-demand threshold environment very even. But when we scale beyond 1K nodes to 2K and 4K nodes, we have to switch to MVAPICH 2.1, which because of the high start times with MVAPICH 1.9, which we are still investigating. So what we boiled that down to is this on-demand threshold environment variable. So because we're using this, it tries to establish all the connections during the initialization of the process. So the numbers are looking pretty good up to 1K nodes, 1K cores. I mean, we do have 2% overhead. We're staying below 2% in most of the cases, which is still pretty high according to me, and we have plans to fix that. Yeah, these are the Rohan numbers with DMTCP without any optimizations. So for 2K and 4K, the numbers in the parentheses are the actual computation time as reported by the application. But if you notice, I mean, the ones outside parentheses are the total times, total runtime, which includes the start time and the actual computation time. So DMTCP is imposing a lot of overhead during the startup. So again, these are very recent results. So we're still investigating the causes of this overhead. So checkpoint times, checkpoint restart times actually. So what we see here is, so we have different problem classes, and we could get a to compile for the same problem class for different number of processes. So you have 3 problem classes here. So within the problem, within the given class of problem, the checkpoint times are roughly proportional to the roughly go down with the checkpoint device size. Um, and the interesting thing over here is so for me, I was expecting, as the number of processes go up, there will be a lot of contention when if multiple processes are trying to write to the disk. But the good thing is that we are using the raster file system at Stampede, which wasn't the case at MGHPCC. So, which I think is, um, um, the contention is not showing up because of the raster file system. So, yeah. So yeah, as I said, micro benchmarks allowed us to focus on some of the different aspects or plugins within DMTCP. There is one performance issue with the Warlock libc column that we identified, and we actually fixed. So it improved the performance by, I guess, up to 70% in some cases. And this issue with of mallocs that we are making the InfiniBand plugin, and as I said before, we're planning to fix that in the fall. So yeah, as is always the case, there are issues while scaling up. This is just a list of some of those issues, some of those war stories, if I may. So we started with a very simple experiment with 2 probes and 4 probes. We had this issue, which is arguably a bug in the raster file system, where multiple processes are trying to call make their system call. Some of them can, even though the directory exists, the system can give us a permission server. So we had to work around for that. And going beyond that, we discovered a bug in the MTCP's code that handles shared memory segments, which we fixed. And beyond 64 probes, we hit this issue with this demand variable on demand threshold. So we have to use this variable. So if we don't use this variable, the application would fail to even start up even without the MTCP. So we obviously work with Jonathan and Harvey on that. So yeah, and when we went up to K-course, we had this issue when MVAPICH 1.9 would take forever to start up. So this is without the MTCP, so we had to switch over to 2.1. So yeah, so we're planning experiments beyond that, and we don't know what issues with it then. So okay, yeah, thanks. Questions?
Any questions for Rohan? People are getting tired. No, we have a question.
Yes.
Oh. So when you go to 16,000 cores, you might have to think about the metadata load and the raster file system also.
Sorry, can you say that again?
You might have to think about the raster metadata load and the raster file system also.
Okay.
Is there some way to schedule some of this I/O so that not everything is trying to write at the same time?
So yeah, that's a good question actually. So right now, so there is a central coordinator with DMTCP, which sends checkpoint commands to all the processes that are running that are part of the same computation. So all of them try to write to the disk at the same time. So as I said before, if you have local SSDs, it might not be a problem, but we'll see how it performs at Stampede.
I'm not sure how many targets they have, but we might also start getting to the point where they're oversubscribing each of the targets also.
Okay.
At 16K, I mean, I think
Yeah.
find it.
Okay. Sure.
Any other questions? Do you have Sure. That's to ask anyone else. Sure.
So I think one of the really exciting things with having the SSDs on the compute nodes is you can save the checkpoints locally, right? Which you can imagine in the future maybe that would allow quicker turnaround between running different jobs. You could sort of swap jobs in and out.
Exactly.
Right now we run one job for 12 hours and then another job runs for 12 hours.
Right.
That means if you have a bug in your program, you have to wait almost 24 hours to figure it out and try to fix it.
Sure.
So the iteration and turnaround time is very slow. So instead, you could run one job for 10 minutes, another job for 10 minutes, another job, right, and swap them in and out quickly. But right now, the resource managers, I don't think, are thinking along those lines. Have you guys
exactly.
resource managers? Yeah.
So yeah, we're thinking about that actually, and that was what Gene's talk was about yesterday. So trying to convert a batch queue into a batch pool. So instead of the linear jobs coming in sequential fashion, you could have a pool of jobs where you could quickly pick one, run for 10 minutes or whatever. High priority job comes, you take a checkpoint, it goes back to the pool, so on. And you could even try combinations of job run combinations of job together such that they don't conflict. So maybe one of them is CPU bound, the other one is bound.
Yeah, so I like that idea a lot. Have you sort of floated it by the Slurm teams or anybody?
I don't think so.
Well, we are not on this specific point, but it's related. Yeah, not on this specific point, but we are talking with some members of the Slurm team right now, and so first we're still working on the basics, but hopefully this will be a corollary in our discussions. Yes.
And I think using the local SSDs would probably get rid of the whole metadata also, like scaling up or whatever.
You said we can use the local SSDs anymore.
Yeah, using the local SSDs will actually get around the metadata issue.
Okay.
Like you won't have this.
So are you suggesting that you start using comments?
Yeah, I was talking to him earlier about comment, but he mentioned that there's been 28 cores.
Okay.
So, yeah.
Okay, any other questions? Okay, so we can't get back to I think we have almost like finished all the presentation. So